Here's something that should bother you. Right now, inside every single atom of your body, electrons are doing something that has no equivalent in anything you have ever seen or touched or thrown across a room. And when I say no equivalent, I do not mean it is hard to picture. I mean the picture itself is the wrong tool. You cannot picture it. Not because you are not smart enough, but because your brain evolved to track lions and berries and falling rocks, and none of those things ever did what an electron does. So let me start with what we think we know. You throw a ball. The ball is somewhere. It travels along a path. You can, in principle, track every moment of that journey, from your hand to wherever it lands. That is the world as your senses report it. Every object has a position. Every object has a speed. These things exist whether you look at them or not. That is the assumption baked so deep into your intuition that it feels like common sense. It feels like the floor under your feet. Now forget the floor. An electron is not a tiny ball. I know that is what gets drawn in textbooks. I know the diagrams show a little sphere orbiting a nucleus like a planet going around a sun. That picture is wrong. It is not approximately wrong or simplified. It is wrong in a way that will lead you to exactly the wrong conclusions if you take it seriously, so let us throw it out. Here's what the electron actually is, or at least what the mathematics tells us it is, and the mathematics has been tested to a precision that would embarrass any other science. The electron, before you measure it, does not have a definite position. It has a wave function. Now that word sounds technical, but the idea is not so scary. Think of it like this. Imagine you have a coin, and instead of being heads or tails, it is somehow both at once, with different amounts of each possibility spread across the coin. The wave function is a mathematical description of how those possibilities are spread out through space. It tells you not where the electron is, but where it has a certain probability of turning up if you go looking for it. And here's the part that twists people up. That spread of possibilities is not just our ignorance. It is not that the electron is secretly hiding somewhere and we just do not have a good enough microscope to find it. The spread is real. The electron genuinely occupies a kind of smeared existence across multiple locations at once. This is called superposition. And it is not a metaphor. It is what the equations describe, and the experiments confirm it over and over again. Now let me tell you about the experiment that really nails this down, because it is one of the most beautiful and disturbing things in all of science. We fire electrons one at a time at a barrier with two narrow slits in it, and behind the barrier we put a detector screen, one electron at a time. You would expect each electron to go through one slit or the other, hit the screen and build up two clusters of dots over time, one behind each slit. That is what a ball would do, but that is not what happens. What actually builds up on the screen dot by dot, electron by electron, is an interference pattern, bands of many hits alternating with bands of almost none. The kind of pattern you would get if you were sending water waves through two slits and they were overlapping and adding together and canceling each other out. But we are sending one electron at a time. There is nothing to interfere with, and yet the interference pattern appears. The only way to explain this is that each individual electron goes through both slits simultaneously. The electron, as a wave of probability, passes through the left slit and the right slit, and those two parts of the wave overlap on the other side, and they interfere with each other, and that interference pattern is what determines where the electron is likely to land. The electron is in two places at once, and the evidence is written on that detector screen. Now you might say, well, let us catch it. Let us put a little detector right at the slits and watch which one the electron actually goes through. And here is where nature turns into something almost personal in its stubbornness. The moment you measure which slit the electron went through, the interference pattern disappears. You get the two blob pattern you expected from the beginning. By the act of measuring, you collapse the electron from its superposition of both slits into a definite path through one slit. The measuring itself changed the result. This is not a quirk of our technology. It is not that our detectors are too clumsy. It is a fundamental feature of how quantum systems work. Measuring a quantum system forces it to choose. Before the measurement, it was genuinely in multiple states at once. After the measurement, it is in one. The act of gaining information about the electron's position removes its ability to be in superposition. Feynman himself said this double-slit experiment contains the only mystery of quantum mechanics. Once you really absorb it, Once it stops seeming like a cute trick and starts seeming like a genuine property of reality, you have understood the central puzzle. Everything else in quantum mechanics is in some sense a variation on this theme. But let us go deeper, because the superposition is not just about position. An electron has a property called spin. You can think of spin very roughly as which way the electron is rotating, though again, rotating is the wrong picture for the same reason a position is wrong. But loosely, an electron can have spin up or spin down along any axis you choose to measure. And before you measure it, the electron can be in a superposition of both spin states simultaneously. Not one or the other, hiding from you, both genuinely until you look. And here's what makes this especially strange. Suppose you measure the spin of the electron along the vertical axis, and you get spin up. Fine, now you measure it along the horizontal axis, you get some result. Now you measure it along the vertical axis again. You might expect to get spin up again, because that is what you just measured it to be, but you do not. The horizontal measurement in between scrambled the vertical spin. The electron is back in a superposition along the vertical axis. Measuring one aspect of a quantum system can erase the information you just gathered about a different aspect. This is not because measurements are violent and messy. It is because different properties of a quantum system are what we call complementary, and the mathematics says you simply cannot have precise, definite values for both at the same time. Heisenberg captured this idea in what we call the uncertainty principle. The more precisely you know the position of an electron, the less precisely you can know its momentum, and vice versa. This is not a statement about our instruments. It is a statement about the structure of reality at the smallest scales. Now I want to address the question that everyone asks at this point, which is why? Why does the quantum world work this way? Why do electrons get to be in superposition while baseballs do not? And the honest answer, the one that I think is most accurate and also most unsatisfying, is that we do not know why. The equations work. The predictions are right to an extraordinary degree of precision. But the deeper reason why nature chose this particular structure, I cannot tell you that. Nobody can. What we can say is that superposition does fade away as objects get larger. This process is called decoherence. When an electron interacts with its environment, with photons bouncing off it, with other particles bumping into it, those interactions are themselves a kind of measurement. Each interaction forces the electron to commit to something more definite. For a single electron in isolation, superposition persists. For a baseball, which is constantly being bombarded by air molecules and photons, the superpositions collapse almost instantaneously, so fast that it is, for all practical purposes, never in superposition at all. This is why your everyday experience is classical. Not because the quantum rules stop applying to large objects, but because large objects are constantly being measured by their environment, billions of times per second, and so they never have a chance to build up any detectable superposition. The quantum fuzziness is always being washed out before it can accumulate. But engineers and physicists today are learning to build systems that stay coherent long enough to be useful. Quantum computers are trying to use superposition deliberately. If you can keep a qubit, which is just a quantum two-state system, in a superposition of 0 and 1 at the same time, you can perform certain kinds of calculations in ways that a classical computer simply cannot. The computation itself exploits the electron being in both states at once. It is not a trick. It is using the actual physics of superposition as a computational resource. And there is one more idea that I find particularly striking, which is the question of what is happening to the electron during the time between measurements. When the electron is not being observed, is it really in superposition? Is the wave function a real physical thing spread through space, or is it just a bookkeeping tool, a way of tracking our probabilities? Physicists argue about this, and the arguments get into deep water about the nature of reality itself. The Copenhagen interpretation, the one Bohr and Heisenberg developed, says that it is meaningless to ask what the electron is doing when you are not looking. The wave function is a tool for predictions, and asking about reality beyond the predictions is asking a question that has no scientific answer. Others disagree. The many worlds interpretation says the wave function is entirely real, and when you measure the electron and it collapses to one position, what actually happens is the universe splits. One version of you sees it here, another version of you sees it there, and both of those universes are equally real. That sounds wild, and it is wild, but the mathematics is perfectly consistent. Neither interpretation has been ruled out by experiment because they all make the same predictions. What we are really arguing about is ontology, what there is rather than epistemology, what we can know and measure. What is certain is that the electron, this basic building block of all chemistry and all matter, does not behave like a thing with a location and a trajectory. It behaves like something for which our everyday language was never designed. And yet the mathematics we have, this beautiful structure developed in the 1920s and refined ever since, describes it with stunning accuracy. We can build transistors and lasers and MRI machines on the basis of quantum mechanics, and they work, which means the theory is not just a curiosity, but a genuine map of how this level of reality operates. The lesson I take from all of this is that nature does not owe us an intuitive picture. Nature is what it is. Our job is to find the mathematics that describes it and to check those descriptions against experiment. When the experiment tells us that an electron can be in two places at once, the correct response is not to find a way to make that fit with our intuition. The correct response is to upgrade our intuition, to let the experiment teach us something genuinely new about what existence can look like at scales our senses were never built to probe. The electron being in superposition is not a failure of physics to find the real answer. It is the real answer. It just happens to be stranger than anything we would have guessed.